Hello everyone, I am Pradeep. I am going to give you overview of radiative heat transfer energy and combustion systems. So you may have come across this situation, and this situation has three questions. Those questions are: How is thermal energy transferred to you? What is the source of the radiation? And what determines how much radiation you receive? And if you're able to give answer or provide the model of a model to these questions, you would able to provide a solution to the some of the extreme engineering problems. One is rocket base plate heating. Rocket is getting thrust due to exhaust plumes, and these plumes are very high temperature and pressure, and rocket base plate is being upstream of the flow. It is receiving mostly heat through thermal radiation, and thermal management is very important for the success of the mission. Another interesting engineering system is the gas turbine, whose heart is combustion chamber, is combustor, and these gas turbine combustion of this gas turbine operates at very high temperature and pressure, and which basically giving a thermal load on the liner of this combustor. And liner temperature is very important. And other a good example of thermal radiation is protection mechanism for the firefighters. So mostly firefighters are receiving the thermal energy through the radiation mode of heat transfer. So our group has developed the radiation in participating media like CO2, H2O, soot particles, and couple it with the Fluent software, and we perform some of analysis, some of the system analysis using these thermal radiation models. So one such system is a can combustor. Can combustor is a academic problem. Can combustor is academic problem which help us to understand the gas turbine combustor. It has a fuel injector through which liquid fuel is coming. One is a primary air is coming through swirler, which basically creating a low pressure zone, and secondary air is passed to protect the wall. And we have utilized the three radiation models: Planck mean model, WSG model, and SLW model. They are of varying accuracy. So, so once fluid flow happens, swirling flow is generated, which and flame length. A flame is only confined to this swirling zone. So without radiation, temperature of this flame is reaching around 2150 Kelvin. With Planck model, this temperature had reduced drastically. It is reduced around 250 Kelvin. A reason being the role of radiation is that it taking away the heat from this flame region and deposit to some other place based on the availability of the participating media. SLW model provides little bit higher temperature than the Planck mean, but still very low to the without radiation model. WCG model basically it gives little bit higher temperature than SLW model. So contours of heat flux demonstrate us that radius near to from radiated heat flux is very high, and total heat flux contours telling us that solar veins is also affecting the temperature characteristic of the on the wall, and it is showing shadow regions. And if we analyze heat transfer rate, a very interesting pictures come out of that. If you look at a wall, that without radiation, it is giving flux is around 706 watt, and with Planck mean method, uh, it is 1073.35 watt, which is around 50% higher. But if you look at the distribution between convective and radiative, and the radiative heat flux is even higher than the total heat flux. To balance the flux on the wall, It is basically convective heat transfer that is opposite to the direction is opposite to the radiative heat flux. However, if we're going for WCG model, it is around 15 times higher than the case of without radiation case. But convective and radiative are both are of the same order, and they are also in the same directions. And while SLW model, it is hardly 10% higher, but radiative is one third of the total. And if you go for if you include the suit further contribute towards the radiative heat transfer, and it is increases radiative heat flux and reduces the convective heat flux. So in this way, it is telling the importance of the radiation. Further, rocket base plate heating problem. So to address this kind of a problem, we have developed a computation domain where there is a nozzle and plume is coming out through nozzle, and there is a rocket base plate, there is a rocket wall, and this is a far field computation domain. And the nozzle are kept at the 700 Kelvin. So these are temperature variation of the plume, and at different altitude like sea level, mid altitude, high altitude. At the sea level, it is very compressed plume is there. Mid altitude is perfectly expanded case is there. However, in high altitude, over expanded case is there. And these characteristics of these plumes are affecting the temperature at the base plate. So at the sea level, first temperature goes down, and then going up, and this temperature is going down. Reason for temperature is going down is that recirculating bubble is formed, and which is cooling the base plate, and also a little bit shadowing effect of the nozzle. However, at the mid altitude, the Planck mean method and SLW method are giving totally different results. And however, at high altitude, the Planck mean method and SLW method are giving the same result, however, with constant difference of the 200 Kelvin. And with this, I will summarize my presentation. Radiation strongly influences temperature distribution and chemical reactions. Radiation contributes more than 50% of the heat transfer in the combustion systems. Radiation governs thermal loading in rocket propulsion systems. Accurate radiation modeling is essential for designing efficient thermal systems. So, thank you for your attention. This is my email ID. Feel free to contact me. Thank you.